In this last video on amines, we're going to be looking at the chemistry of aryl diazo compounds, these aryl diazonium salts. This means our diazonium salt is directly attached to an aromatic ring. And we're going to look at the spectroscopy of amines, and then we're going to look at some practical things associated with amines and pharmaceuticals in general. Okay, when we have a primary arylamine, like we see here, all right, now you're going to treat it with nitrous acid, and remember nitrous acid is just the combination of sodium nitrite and an acid. You're going to get an aryl diazonium salt, and this is a reasonably stable compound. You can isolate it. You can, I guess, hit it with a hammer and things like that and it'll explode, but it's a relatively stable compound as far as the other diazonium salts that you saw previously when alkyl groups are attached to the diazonium salt. Okay, this aryl diazonium salt turns out to be a very useful compound. It can give you access to a variety of other aromatic systems. For example, the reaction with water and heat converts the diazonium group into a phenol and generates nitrogen as a byproduct. The reaction with HBr puts a fluorine here, and note that these are the first reactions that we've seen for benzene rings that would put an OH on a benzene ring or put a fluorine on a benzene ring. We didn't see any reactions back in the electrophilic aromatic substitution chapter that did that. Okay, various copper salts will turn the diazonium group into the corresponding halogen group. Okay, so we could treat this with cuprous copper 1 iodide, chloride, bromide, or cyanide, and this would replace the diazonium group with whatever our counterion is for copper 1. We don't actually have to have copper 1 if we want to make an iodide. In this, with iodides, you can use sodium iodide or potassium iodide. Okay, if you want to reduce the diazonium salt back down to a corresponding hydrocarbon, you can use hypophosphorous acid. Ideally, we don't really want to use this reaction because it just took us back to where we came from, but sometimes it can be necessary to do things like that. All right, if you're looking at these reactions, the mechanism, it's as if it's reacting like this compound here, the phenyl cation. The mechanisms in these cases are a little bit more complex, but and we're not really going to go through them, but you can think of it as being the source of this. I believe the mechanism here is kind of like the nucleophilic aromatic substitution that you saw way back in the first half of the class. Okay, all right, so let's look at some of the things that we can now do. Okay, back in the electrophilic aromatic substitution reaction, there are questions I could have put on the exam that you could have not answered. Here's a simple one right here. How do you convert benzene to phenol? It's still one of the hardest, or a relatively hard synthetic transformation to do. Okay, but let's look at how you do that, how you could do that using the diazonium chemistry. All right, so the clue to use the diazonium chemistry comes from the fact that this is a phenol, and we really have never seen any other reaction that directly puts a hydroxy group on a benzene ring. So we know that we're going to have to use the diazonium salt. Okay, so this means that this is going to have to come from that. All right, so this is how we have to do this. Okay. In the last step, we're going to treat the diazonium with water and heat. The diazonium has to be made from the reaction of a primary arylamine, in this case aniline, with NaNO2. Aniline, recall, we have to make by reducing the corresponding nitro compound, which has to be made by electrophilic aromatic substitution in a nitration reaction. All right, here's another problem here that if I put it on the exam a long time ago, you would have become very frustrated because you realize that you could not do it. Okay, how do you make meta-dichlorobenzene? Okay, recognize that electrophilic aromatic substitution can't do this because chlorines are orthopara directors. So we can only make orthopara if we're going to restrict ourselves to using chlorine and FeCl3 as our reagent for introducing the chlorines. All right, but we can do this using the diazonium chemistry. Okay, so if we were to, in the last step, treat this diazonium salt with CuCl, we would get the meta isomer. So now where does the diazonium salt come from? Okay, it comes from these three series of steps right here. Okay, we'll just look in the other problem. We have to do a nitration, nitro to amine reduction, and amine to diazonium transformation. Somewhere also in this, we're going to have to work out the introduction of a chlorine. Okay, all right, so the diazonium salt can only come from the corresponding aniline derivative, which would be metachloroaniline. Okay, all right, so now that we have this, we're torn. Do we nitrate first? Sorry, chlorinate first, or do we nitrate first? Well, the reason, because these are meta, we're going to have to nitrate first, right? Because only by having a nitro group on the benzene ring already can we get something in the meta position, all right? Okay, so before we reduce, we're going to have to add tin and HCl, and that's going to turn the meta-chloronitrobenzene into the corresponding aniline. Okay, all right, and now we know that if we have nitrobenzene and we do the chlorination, it's going to go meta. Let me call this step A and this step B. What would happen if we reverse step A and B? Okay, so let's hypothetically reduce. Okay, that's going to give us aniline. And now let's hypothetically chlorinate. And remember, with aniline, it's so activated, we don't really need the FeCl3. All right. Here we see the problem. We're going to get para. So we can't do that alternate route. It's very critical that we chlorinate before we reduce. Otherwise, the chlorine is not going to end up on the right carbon. Okay, let's do a couple of synthesis problems. Outline a sequence of reactions that will convert nitrobenzene into each of these compounds. Okay, and we know that we're going to have to use the diazonium chemistry, right? Because the nitro group isn't there anymore. And we know the diazonium chemistry is the only thing that really transforms it to something else other than an NH2 group. All right. We also note that we have a phenol, a group that we didn't really see any way to introduce back when we were talking about electrophilic aromatic substitution many months ago. And we see a nitrile. again, a group that we don't really know how to directly introduce. We could make it from a carboxylic acid or something, but it's not going to be an easy group to introduce unless you use the diazonium chemistry. Let me just say one thing. Maybe I forgot to say it a few slides ago, but the diazonium chemistry is sometimes referred to as the Sandmeyer reaction. Okay. All right, so let's look at the first one. All right, the phenol OH is a very strong ortho-para-director. So we know that OH can't be on there when we add bromine. So it's going to have to be something else. Okay, so let's do the diazonium to phenol conversion last. All right. Okay, bromine is meta on here, so we're going to have to add bromine sometime while we have an electron withdrawing group like a nitro group on the benzene ring. All right, so the best way to do this is to brominate nitrobenzene. It's going to go meta, and that's going to give us meta-nitro bromobenzene. Okay, we're going to reduce the nitro to the corresponding NH2, turn the NH2 into a diazonium, and turn the diazonium into a phenol. Okay, this other problem here, that we have a para arrangement, so we're going to have to change the sequence of when we brominate. We can't brominate when we have just a nitro group there. Okay, and we're going to have to change the reaction that we use to quench the diazonium. Okay, we're going to have to turn the diazonium into a cyanide and not a phenol, which we can do with copper 1 cyanide. Okay, so there's our last step, treating the diazonium salt with copper 1 cyanide. Okay, and what we do here is we reduce the aniline to make the diazonium, but we have to add bromine while we have an electron donating group on our benzene ring. Okay, we can't do it when there's a nitro group. Okay, and this is a ortho-para director. I know earlier in this chapter we looked at how anilines can be problematic, but we'll just say in this one we're going to be extremely careful to add bromine very slowly and add exactly the right amount of bromine. Okay, all right, so we have to add bromine here, and then so the first thing we're going to do with the nitro compound is we're going to reduce it with tin and HCl. Okay, so the first thing we're going to do is turn nitrobenzene into aniline, and then we can put the bromine in the right place and use the Sandmeyer sequences to introduce the cyanide. Okay, let's look at another reaction that diazoniums do, and this is kind of not a very general reaction, but it's a reaction that really put organic chemistry on the map. Okay, so in the 19th century, one of the first uses for organic chemistry was in the dye industry, and it was discovered that if you take a diazonium salt and an aromatic ring that's extremely electron rich, it has to be at least an OR or an NR2 group here, or an OH or an NH2. Okay, when you do that, you make this type of compound known as an azo compound, and depending on the groups on the benzene rings, you can get some very exotic colors. Okay, and these again are the first commercial dyes. They're still used in dyeing fabrics. and in some cases as food additives. Some of these have turned out to be carcinogenic, but with a lot of research, we know which substitution patterns produce carcinogenic compounds and which do not. So the ones in use are quite safe. Okay, the mechanism is just electrophilic aromatic substitution, ortho or para to this group. Okay, so the arrows I'm using here are going to give us this Meisenheimer complex or intermediate of electrophilic aromatic substitution. We just lose the extra proton to regenerate the benzene ring, and that gives us an azo compound. This mechanism here should not be new to us because it's the same as the classic electrophilic aromatic substitution reactions that you saw in the first half of the class. All right, so let's look at a few equations here. All right, so this zwitterionic diazonium salt here will react with this electron-rich compound to make the anionic diazonium salt that you see here. If we treat this diazo compound with dimethyl aniline, we will produce the azo compound here. And again, notice that what happens here in each of these cases is that this group ends up para to the electron donating group on the other ring. Okay? All right, that's the best way to remember that reaction. This whole unit ends up. The only thing that changes about the diazonium salt is that the triple bond nitrogen-nitrogen triple bond becomes a nitrogen-nitrogen double bond. Okay. All right, let's look at the spectroscopy of amines. And what we're going to see is that they have the same basic trends as alcohols and ethers. The NH stretch is intense, but it's not as intense as the OH stretch, and this is because there's not as much of a dipole with the NH bond as with the OH bond. And in NH2 groups, we see that the NH stretch is split into, okay, I'll just go ahead and call it a doublet, but it's split into two halves or two peaks instead of just one. And it occurs somewhere between 31 and 3400 wave numbers, somewhere between where the OH comes and where the CH comes. Okay? In the proton NMR, we see the NH peak occurring somewhere between 1 and 5 parts per million. This is a very large region, and it's usually broad due to hydrogen bonding and due to the fact that one of the major isotope of nitrogen couples, but not, or has an NMR signal, but not in the same way as a proton or a C13. It's a little bit more complex. Okay, there's no coupling to the rest of the molecule, just like with the OH group, and this is true in most cases. Occasionally you can see coupling, but usually the NH is isolated from the rest of the molecule. The NH in arylamines and amides occurs at a much higher value, typically 6 to 10 ppm. And the peak adjacent to the nitrogen is a little bit higher than what you typically see for all carbon and hydrogen systems, okay, but it's not quite as high as you would see as if this were an oxygen or a halogen there. Okay. In C13 NMR, if we have a sp3 carbon attached to nitrogen, the chemical shift is 35 to 60. And recognize that at the lower end of this range, it's really hard to distinguish this from a regular sp3 carbon that's only attached to either carbon or hydrogen. Okay, so only the higher ones are really distinguished. All right, so let's look at a few examples of spectra. Here's a hexylamine, and here's our NH stretch here. Notice how it got split into two little peaks. Okay, here's now an NH, a nitrogen with only one hydrogen, and we still see an NH stretch, but it's not split. Not quite as large as the OH stretch, if you remember those, but it's usually quite noticeable. Here's a tertiary amine. And a tertiary amine has no hydrogens at nitrogen, and thus we see nothing of significance in that region right there. Okay, let's look at the proton NMR of this compound. We'll also look at the C13 NMR. This is N-ethyl aniline. Okay, so here's the NH right here. Okay, what you see is that it's a broad singlet. It's not coupled to the rest of the spectrum. This CH2 group here looks like your classic quartet. Okay, not really showing any sign of coupling to the adjacent NH peak. It's coupled only to the CH3 group of the methyl group. So this ethyl group looks like your classic ethyl group with a quartet and a triplet. Okay, this one has a higher chemical shift of about 3 parts per million, which is consistent with it being adjacent to an electronegative atom. But remember that with an oxygen or a chlorine, the chemical shift would probably be higher than it is here. Okay, here we see the C13 spectrum. And here's our nitrogen carbon. And what we see here is that it's coming at about 38. It's kind of coming at the lower end, so it's really hard to distinguish this from like any other sp3 carbon that doesn't have an oxygen on it. Okay, so it's not really well distinguished. Okay, let's do a spectroscopy problem. Assign a unique structure that has that formula C6H15NO and it's consistent with the spectral data. First thing you should always do is calculate the degrees of unsaturation, and remember that we drop the oxygen, subtract a hydrogen, and we're going to use C6H14 as our formula for the unsaturation calculation. So rings plus multiple bonds equals 6 times 2 plus 2 minus 14 over 2. And if you look at this equation adds up to 0. This is a molecule that has no multiple bonds and no rings. Okay, so it's a completely acyclic molecule without any rings or double bonds. It does have an oxygen and a nitrogen. Okay, what we see here is our split NH2 group, so this looks to be an NH2. There doesn't seem to be an OH, so that this means that the oxygen part of this is an ether, not an alcohol. All right, so we have a doublet for 6 hydrogens. This is, you've seen this before, this is almost always an isopropyl group. Okay, so where's this hydrogen here? Well, this hydrogen should have at least 7 lines, And the only thing we see that's consistent with that is this peak right here, which it's a given that it's a septet. Okay, this high chemical shift is suggestive that it's on an oxygen. Okay, we have another peak here that looks like it could also be on an oxygen, and that's a CH2 group, or it's two hydrogens adjacent to two other hydrogens. Recognize that there's 6 hydrogens, and we have found 1, 2, 3, 4, 5 of them. Okay. All right. So all that's here, we have a broad singlet, 2 hydrogens that's kind of hiding with this peak. That's our NH2. We have 1 more carbon. This is the only logical structure that we could have from all of this data combined. Okay? All right. This is an editing that I don't agree with. Okay? This was edited out of this textbook, but it's probably an important reaction. So I'm going to go through it. All right. So an interesting reaction is the Hofmann degradation. And in the Hofmann degradation, we actually lose a carbon. Okay? And this carbon goes away as carbon dioxide. All right, so how does this happen? All right, bromine, sodium hydroxide, water. This is the only acidic hydrogen. Okay, so what we do is we remove that hydrogen. Has a pK of about 17. We make the anion. Okay, the anion gets brominated to make the N-bromo amide. This is even more acidic now and reacts with hydroxide ion again. And when it does this, it undergoes a 1,2 shift of the alkyl group. Okay, so we see the cyclohexyl group goes from carbon being bound to the carbonyl group carbon and is now bound to nitrogen. This lone pair at nitrogen is going to come here and make a double bond. So we have a nitrogen carbon double bond now, and bromine is going to go away. And this gives us this. This is called an isocyanate. An isocyanate is an unstable compound. It reacts with water, spontaneously adds water to make a carbamic acid, which is also an unstable compound, as if there's an active hydrogen right here. And this is unstable because loss of carbon dioxide is so facile to just produce the free amine. Okay, so the net result is that you lose the carbonyl carbon and create a new carbon-nitrogen bond directly to whatever was bonded to the carbonyl group originally. Okay, all right. Related to the Hofmann degradation is the Curtius-Schmidt rearrangement. Okay, so what we do here is we take not a amide, but we take an acyl azide, and we're going to heat it in water or an alcohol. And in water, we get the same thing we do in the Hofmann degradation. But if we use an alcohol, we're actually going to get a stable carbamate, which is often referred to as a urethane. Okay, how does this reaction work? Well, we're going to write a resonance structure, and hopefully you see some commonality here. What you see here is an anionic nitrogen. We have a leaving group, nitrogen itself, which is just like this one here, which also has a leaving group. Okay, so the same process is going to happen. The isocyanate is generated in water. It reacts to make the free amine, but in ethanol, it doesn't make a free amine. The ethanol adds, and we get this stable urethane right here. Okay, So urethanes are very interesting, very useful compounds. Let's look at a couple of applications of them. Okay, this is the pesticide aldicarb, which has been associated with the worst industrial accident in history in Bhopal, India, like sometime in the 1980s. Okay, so this herbicide recognized has a urethane group here, and it's just made by taking the oxime here and treating it with methyl isocyanate. Okay, and this accident happened because water got in the isocyanate tank, and when that happens, of course, it's going to make methylamine and CO2. And both of these compounds, methylamine and carbon dioxide, are gases. Okay, so when you have 1 mole of methyl isocyanate, it needs about 50 mils. And a mole of water needs about 18 mils. But according to the ideal gas law, if these become gases, we now need 44.8 liters. So there's a tremendous expansion of volume, and the container could not handle it. Okay, this is done by Union Carbide was the company. They claimed that it was sabotage. The government of Bhopal said it was just a crappily designed plant. Okay, so I don't think it was ever officially resolved. I know that Union Carbide is now out of business. I don't. They've been folded into some other company. I don't know which one, and they did pay a humongous fine, but they have been doing this process safely in West Virginia for more than 50 years without any sort of problem. Okay. All right, so many of you probably heard the term polyurethane. Okay, so let's look at spandex. What is spandex? Without isocyanates, we could not have spandex. Okay. All right, so spandex is the polymer that you get from taking toluene diisocyanate and a polymeric alcohol. All right, and this makes a polymeric urethane because you have 2 functional groups here and 2 here. When they react, they make a continual chain. Okay, and this chain recognize that it has some of the same conformational properties that rubber does, and the chain can basically, let's see, not totally sure why you get the stretching properties that you do with spandex. I think there's weak hydrogen bonds that you can easily disrupt by just pulling on the ends of the molecule, and that's how you get the properties of spandex. Okay, so let's look at another aspect of amines, and this is that amines are very common components of pharmaceutical compounds. Okay, so I'm going to use morphine here as an example here. All right, so morphine it's kind of it doesn't have a long shelf life, and this is because when you have an active amine with a lone pair, in the air and light, you can get an air oxidation to the imine, which will then, in the presence of water, hydrolyze to the aldehyde. So this is a process that's occurring very slowly with any free amine. Okay, and because of that, because so many pharmaceuticals are amines, They're not sold as the amine. They're sold as the ammonium salt. So this is how you would get morphine if you were ever given a prescription for it. It would most likely come as the hydrosulfide. Sometimes it comes as the hydrosulfate salt, sometimes as a citrate salt. All of them have different solubility properties, but I'm just using the adduct of morphine with HCl to illustrate this. Okay, so this will now have a much longer shelf life because the nitrogen lone pair is gone. Okay. All right. Morphine is also protonated at biological pH, so this causes a problem. It doesn't cross into the brain quite as fast for that reason. For that reason, about 100 years ago, someone had a really good idea that if you acylated morphine, maybe you could reduce its polarity a bit by turning the OHs into acetate esters. Okay. And this is the well, it's actually not a pharmaceutical, it's heroin. Okay. So it was actually a product of rational drug design. It was designed to be a faster acting version of morphine. I guess you could say heroin was a classic idea or a classic example of a good idea on paper that just didn't pan out the way it was intended. Okay, let's look at another pharmaceutical. Sorry, this is not a pharmaceutical. I don't think you could ever get a prescription for cocaine, but this is how cocaine comes. It's a solid, crystalline solid, and it usually comes as its HCl adduct or its hydrochloride salt. As the hydrochloride salt, it's a lot more stable, has a longer shelf life, but it's also not volatile. This is because it's an ionic compound. Okay, so it's harder to vaporize. So what people would do to make it more volatile and to make it smokable or whatever is to add sodium bicarbonate to it, and the sodium bicarbonate cocaine mixture is known as crack. Okay, and so the idea here is that you convert the HCl salt to the free base, and this is another term you may have heard, free basing. Okay, this makes it more volatile and makes it into a more smokable form. Okay, so that's what the idea behind crack and free basing is to just remove the HCl from the cocaine. Okay, all right, so cocaine is local, also has a lot of interesting pharmaceutical properties. It's a local anesthetic, so someone thought, okay, let's see if we can get the local anesthetic property without the feeling of euphoria and the rapid heartbeats that would be associated with cocaine itself. And this is the drug Novocaine, which is used in dental procedures and local as a common local anesthetic. And what you see here is that it has some of the basic framework of cocaine. Like right here, you kind of see that we have the same relationship, right? And so I guess if you go, next time you go to the dentist office, you can think about you're looking at something or you're using something that was inspired by cocaine, I guess. Okay, so we can make, just because cocaine is undesirable doesn't mean that we can't use it as a lead compound to make useful drugs, because it has a lot of very interesting biological properties. Okay, let's look at another classic example of drug abuse, and this is has to do with a TV show on AMC called Breaking Bad, and this is the classic way you would turn the decongestant pseudoephedrine or Sudafed into methamphetamine. Okay, all you have to do is you just got to knock out that hydroxyl group there, and that turns Sudafed into methamphetamine. And what would classically be done here is that we treat it with phosphorus and HCl, and that's why you would see people go to Home Depot and buy tons and tons of matches for the phosphorus and lots of muriatic acid for the HCl. Okay, but an effort has been made to control methamphetamine by controlling the supply of Sudafed. So now you have to go ask the pharmacist for Sudafed. Okay, so in the TV show Breaking Bad, that created a problem in the early season. Okay, and so this fellow here, his responsibility was to supply the Sudafed. He's telling his boss that he couldn't get it because all the suppliers got busted. And then his boss said, well, screw that. I'm just going to make it through reductive amination of phenylacetone. And this was, to every organic chemist, this was a really great line because we probably all were already thinking the same thing. Okay, so in the early seasons, the methamphetamine is made from Sudafed. In the later seasons, it's made by the process that you see at the bottom. Okay. One thing you'll probably notice about this fellow here is that he cannot correctly pronounce the name of that compound. It's methylamine, not methylamine. I don't know who would call it that. Okay. All right. There's one thing about this that I always found puzzling that the show really didn't address. This is, let me see, can I still remember how to assign RS configurations? Priority 1, 2, 3, 1, 2, 3. Looks R, but hydrogen is out. So this is S. All right, this could only be racemic. All right, so I don't know the full pharmaceutics of this, but it seems like the meth made this way would not be as good as the meth made from Sudafed because it is racemic, and if only the S enantiomer is working to produce the effects of methamphetamine, the R would just be kind of wasted space. Okay, all right, you need twice the dose to get the equivalent. High. All right, so anyway, I think this is the